Hello there, this is Hans Forschner with Navcon Engineering Network. The intent of this video is to give an overview or general overview of the SoundPLAN noise modeling software. The SoundPLAN software has a long history. It goes back, I think the initial development were done in 1985. The first DOS version was released in 1986. And we are now at SoundPLAN version 9, which was released in January 2023. Here are some copyrights and disclaimers. No warranty of any kind with regards of the material included, but also not limited to the implied warranties or fitness of for particular purposes. Again, this is a general overview to get a sense on the software concept and structure. Before we get started, a quick side note to make sure that we are on the same page in terms of simulation, motivation, and recent history. So, of course, the motivation of simulation is we want to improve the design speed, cost, the quality of engineering. We want to introduce assessments of the design or what is planned and be able to modify if necessary. It provides compliance verification like ordinances, CEQA, or 23 CFR for freeway noise. We can do optimization of the impact in terms of noise control mitigation, site assessments, develop options, identify problems, and give feedback to city planning. The recent history, maybe the history for the last 50 years, started, of course, with hand calculation, with little hand calculators, continue with spreadsheets or lookup tables, then DOS, Fortran-based codes, and then, of course, commercial software products were developed when Windows came out and personal computers were available. And at the beginning, of course, manual input, and nowadays a lot of interfacing to GIS programs, AutoCAD, aerial photos, OpenStreetMap, and other programs. What is the definition of the model? Generally, a model is an abstraction for an intended use. So we are trying to represent certain characteristics of the real world. In terms of noise, of course, the objective is to develop a model for freeways, buildings, topography for different sources. And we abstract everything in terms of point, line, and areas, objects that have certain relations and parameters. In terms of a mathematical model, the mathematical model defines equations, different boundary values, initial conditions, and the model data is basically described in this conceptual model and the propagation standard. The mathematical model is basically the mathematical equations, the boundary values, sometimes the initial conditions, the model data that describe the conceptual model. And here we have basically the propagation standard that describe how the propagation works. The computational model is basically the implementation of the mathematical model. That means all the algorithms are implemented. In some cases, there's certain convergence criteria, and all of that, like the SoundPLAN software, could be also looked at as a computed engineering application that implements the mathematical model. The conceptual model, that is what I relate to the project model. So when we create a SoundPLAN model, that is a conceptual model. It collects all the assumptions or planning parameters. We are using algorithms or relationships of different objects, and the data describes the reality as we want to define it for the model. And of course, the mathematical model can be verified. We can do certain validations, do experiments, to see if the project meets the intended use. And in some cases, we may want to modify that for other uses, other temperatures, other wind conditions, or other operational conditions. So here we have a basic schematic of an outdoor noise propagation model. We have the factory, we have the different sources, we have the propagation path and the receivers. So we are basically analytically representing these different objects with noise sources, objects that are defining the noise sources, the propagation in terms of barriers, berms, reflective surfaces, buildings, walls, the topography with elevation lines or elevation points, and meteorology conditions, temperature, humidity, wind, etc. And of course, the receptors could be on a building, could be free field, could be the property line. That is kind of where we will do the prediction to. Here we are seeing the SoundPLAN Manager, which is, I also refer to as the project gateway. So here we have different like functions in terms of project definitions, settings, and predefinitions of standards and all that. And then here we have the gateway of different subprograms. So here on the left, so basically it starts from the left, goes all the way to the right. On the left, we have the Geo-Database and the library. We have the calculation kernel here, the little abacus icon. And then we have different results, spreadsheets, and the graphic representation of the results in graphic forms. And then we have various optimization programs down here. I will discuss the wall design and the expert industry later in this video. Down here at the bottom, you see a certain project description, and in this case, for this specific project, what are the relevant standards that are selected currently as a default. Here we have a general flow, data flow diagram. On the left-hand side are just some of the basic steps, the resources, the definition of the acoustical model, the processing of the data, and the results, presentation or documentation. The resources, of course, could be a digitizer, could be noise source data in terms of electronic files, DXF files, shape files, Excel files, Oracle, OpenStreetMap, Google Maps. All of this, of course, needs to be collected before we start with the project. Some of that is always available, like the Google Maps and the topography. We can get that information pretty much worldwide. OpenStreetMap could be also readily available. But in terms of the noise sources, we need to get that feedback either for traffic or for the source definition for construction or whatever model you're creating, the information about the noise source, sound power, or traffic information. All of the resource information that will feed into the acoustical model. So here we have the Geo-Database and the library. The Geo-Database, we'll find out, has different organization tools. There's the situation, and then we have the geo-files that I also refer as layers. And the geo-files we can compile to different situations, so we can have multiple names of different scenarios or situations in a project, like existing, future with noise control, or with different roads or different traffic or whatever combination we want to analyze or simulate. Then, of course, we have other objects that define the path and the receivers. So this is a big chunk of the software development is the development of the acoustical model in terms of the geometry and the acoustic parameters. When a situation is completed, we can go to the run kernel where we have the program process that information automatically based on these mathematical models that are defined in the different standards. So based on the noise source, the standards are linked to these sources. The program will predict the noise levels at these receivers. the results will be generated, graphic files or the input for graphic files will be generated, or outputs will be generated for the wall design or the optimization of walls or the expert industry. Now, these two optimization programs, the results can be again saved back into the Geo-database for further calculation. Here we have another flowchart to emphasize the concept of the data structure and data management in SoundPLAN. So we have 3 levels of organization. We have the objects here at the very top, objects that define the elevation, the buildings, all the sources, the noise control objects, and the receptors. From the elevation, that's the spot heights and elevation lines, we can generate a digital ground model. So that DGM stands for digital ground model. And with combining the different objects into these different layers, so here we have the black, blue, and red lines, so these could be different layers of information, we can organize certain situations. So that's the 3rd level, different situations that are compiled by different geofiles or layers. These situations then can be put into the calculation kernel, and then we run the different predictions of these situations. Here, another way of visualizing that example of a current plant. So that's the name, situation 01 current plant. So here we have the noise sources, point and line sources. We have structures in the plant that could be buildings. We have receivers at the property line. And then we have the digital ground model that's based on elevation lines and maybe some spot heights. So with these 4 layers, the program can do a prediction for these receivers. And then we can create another situation by just adding additional layer to the situation. And then we have, for example, a layer with additional sources. So that could be a future scenario with additional sources. And then we can add another layer into that, and that could be a noise barrier. So with that, we have 3 different situations, the baseline, future, with additional sources, and future plant with noise barrier. Here we have the Situation Manager, which is a very integral part of the program, where we can organize the information that we have. The concept of layers is very widely used. GIS programs, AutoCAD, any type of drawing package has this concept of defining different layers of information. By organizing the different objects into different layers, we can assemble different scenarios. So here we have on the left-hand side here, we have the different situation. If you look at my naming convention, I use alphanumeric naming convention. So with 000 base model, I have a base situation that probably has all the geofiles included. 001 is the road noise, and then I have several road noise situations with different configurations of traffic, current traffic, future traffic, or for wall optimization, a layer with a wall that is being optimized. There's other situations for construction noise, railroad noise, wind energy, go-kart racetrack, and so on and so on. So here we can see in the center the layers that are currently assigned to this 01 road noise situation. And then you can see all the other geofiles or layers that are currently in this project. On the very right side, you see a preview, text that we can put in there to describe what's in this layer. And at the bottom, we see another details of when was it changed the last time. Here we have a quick overview over the Geo-database. There's a graphic user interface. The basic the menu option is File, which gets us back to the File Situation Manager. And then here we have the Start option. And the Start option gives us these ribbon up here at the top with the objects here on the top left side, view controls, the viewports or bitmaps. So here if we add bitmaps in the background, we can add new bitmaps, and we can also combine them to group them. There's different input functions, select function, and edit functions. Here on the right-hand side, we have different zoom, rotation, and reset buttons. And overall, this is the entire workspace with a status line at the bottom. And here on the left-hand side, we can dock different windows with different information. So here, for example, the information that we see here is the Geo-file manager. That gives us the organizational structure of different geo-files. And there are several parameters that we can select for each geo-file. We can lock a geo-file. We can turn it on to be seen or not seen, or we can hide it. The same for objects. That's right below that, object types. So each layer can have a combination of different objects, or it can have just one object in it. It really depends on how the data is organized. Here we have the fundamental ribbon. This is has similarity in terms of the top, the objects and the view control, but then we also have import-export option, the DGM options, and online map options. So this is the interface or the option to open up Google Maps or OpenStreetMap, and then also some coordinate systems settings right here, where we are defining the reference and coordinate system for the project. Here, these the graphic user interface with the tools. These are, again, more extended tools to modify data, especially when we start importing information. We can modify them. There's some geometry tools like right angle mode, adding points, reducing points, filtering points, connecting. There are all kinds of building tools, height tools, and general other tools here. And then there's various other menu options with defaults, logbooks, and the docking of windows. Here is an overview of all the different objects. Just as a preview, here we can group them by general sources, airport noise source objects, environmental objects, receivers, and generic tools. So here we can add a tape measure, we can add a camera, animation path, and other parameters that can be used for different functionalities. In terms of the receiver, there's the single, the grid map receiver, and a cross-section. So single point is just a single point. Cross-section is a minimum of 2 points, a start and end point. For the grid map, we need at the minimum 3 points to define a triangle. Ideally, it could be a rectangle, but it could be also a circle. In terms of the environments, objects, there's line, point, and areas objects that we have here that have different attributes, of course, to define the different characteristics of these objects. In terms of the sources, we'll get to that in a second. Point line area sources, industrial buildings. Again, we have to have the information from the client in terms of what type, how noisy that source is, what's the spectrum. If they don't have that information, then we can go back to the library in SoundPLAN to assign known or some default numbers for the power levels. Here are some view controls, very important to basically visualize the consistency of a model in terms of spatial distribution, elevation, and then we can either do that with a top view or certain side views, side or front view, or a 3D model when you have the digital ground model. These are different other options in terms of the start ribbon to select or to edit different objects. Again, we manipulate information, especially when we import that. They may not be in the right format, or they don't have the right attributes. So it's important to have lots of editing functions to manipulate and get that to be consistent with the model. Here under fundamentals, the import, we can import the SoundPLAN models from other projects. There's other interfaces like TNM, OpenStreetMap, or CityGML, or S3 shapefiles. Some of them require additional interfaces, like TNM 2.5 requires you to have the software installed on that same computer. For TNM 3.1 interface, you don't have to have TNM installed. As long as you have the TNM project, you can import that, and of course you can export your SoundPLAN model back to TNM. Digital ground model. This is where we calculate the digital ground model. Again, under the fundamentals, we load or have the program load the points or elevation lines and create the triangle base to create a digital ground model. Note here, we can also include objects like roads and railroad tracks, or parking lots or other objects, where the elevation of these objects or the side of the road can be used as a parameter in the calculation of the digital ground model. Here we have the general input window for point source. This is just to kind of show you the general layout of objects. We have typically a name. We have the Geo-file where this object is assigned to. And then we also have, if there are multiple objects, the option to jump from one point to the next. That's these blue arrows here in the top right corner. Then below that, we have different tabs. Here, this is the general tab for point source, where we can define a spectral information from the library. We can assign a time histogram, what is the operation of that source. And then, of course, here the sound power level, different other correction terms. And then down here, we have the geometry. The geometry can be in terms of absolute or relative elevation. Absolute is absolute height above sea level. Relative is always the relative height above the digital ground model. So in some cases, it may be advantageous to use the relative height as you have a digital ground model. So you only have to, in this case, this is a stack. So the stack is 35 meters above the ground. So as long as the program knows that the ground is at 120 meters, we know the sea level, the absolute height is 155, and the relative height is 35. So additional parameters for sources, of course, the spectrum. So here there are libraries. SoundPLAN has 3 libraries: a system library that comes with the installation of the program. It has a project library that is generated as you develop your project. And there is a global library. The global library is something the user can generate. So as you develop new projects, add new sources, you can copy those into a global library, which then are available for within your company. And so you can move around these global library information from one project to another. The system library cannot be modified, so this is, again, specifically something that SoundPLAN offers. Again, there is no warranty with this data. SoundPLAN uses references from published information from standards and define these system library information based on these publications. So in terms of the source input, one of the information that we can apply to a point source or line source, area source, is the directivity. So here we have a stack. So we have a 3-dimensional directivity assigned to that. And so here we have the library for the directivity. And here we can assign that in the source and rotate that directivity. In terms of the stack, of course, the directivity is pointing upwards. So here we have a vertical directivity. Here's the horizontal directivity, and here's a roll directivity. A roll is probably not used that often unless you have like a music venue with speakers in it. For the most part, you are rotating either in horizontal or in vertical direction. Then in terms of road input, road standards typically define the emission based on a reference level at a certain distance, a lot of times 50 feet or 25 meters or 15 meters. In terms of the input, we enter the center line of the road, sometimes the road spacing, and we are assigning how many vehicles and do we have per hour, per day in the different assessment periods, what's the speed, and what's the road surface. For the TNM input, we also need to put in the road width. With the road width, the program has information about the reflective road surface for the modeling. Now here we see at the bottom the geometry. So road inputs typically are polylines. So we start, and on the first point we define all the attributes of the emission and of course the height and all that. And then we digitize the following coordinates. Whenever something is changing, then we add new attributes. So if the road gets wider, we can change the road width or the cross section to the right and left of the center line. Or if the emission is changing, the traffic volume, you can change that. And whenever there's a change, we'll see that there's a blue text here in the table. And so some of the changes could be also a bridge. Where's the start of the bridge? Where's the end of the bridge? SoundPLAN will automatically define the source heights for the road sources. For TNM, there are basically 3 heights. For cars and medium trucks is 0 and 5 feet. That's 0 meter and 1.5 meters. And for heavy trucks, it's 0 and 12 feet. So 0 meters and 3.6 meters. So those source heights will be automatically defined by SoundPLAN. Here are just some of the tabs. Here's the emission tab. So we have multiple inputs option from road time histogram to vehicles per hour, manual input, but we can also do percentage manual based on the average daily traffic. Then here another tab is for speed and surfaces. So here we have pavement types, control devices, and again down here we have the geometry. One thing I want to note here at the bottom, there's different arrows, these blue arrows, double arrows, and an arrow with a line on the left or a line on the right. Those are different functions to jump to the next attribute change. So the double arrows always jump to the next attribute change. The arrow with the line to the right is jumping to the end of the polyline, and the other direction with the line on the left, it jumps to the first coordinate of the polyline. And then the minus sign here is to remove a coordinate. This little icon here on the left-hand side that looks like a tree allows us to look at the function of the parameters in a different view. And so we can actually see from one attribute change to the next, what is the change of the attribute. So we don't have to change all the attributes. So if we just change the road width, then on the second blue line where the road width is changing, SoundPLAN will only change the road width. Everything else stays the same until the end of the road. So that's the same process for any other line objects. Things are changing on a polyline until the line ends. Here we have an input window of a receiver. Receiver, of course, is a point. So the attributes are the name. We can, again, assign it to Geo-files. We have, of course, attributes in terms of the distance to a facade if the receiver is on a building. how many floors we want to calculate. So we can calculate up to 255 floors. What's the floor height, incremental floor height, and then what is the labeling of the floors. So when we have several of these objects included, like the sources, the receivers, any type of intermediate objects, the calculation areas or ground, then we can do the run calculation. And the run kernel in SoundPLAN, there's a batch processing capability, so we can run different runs one after the other. They are controlled with a check mark here in the front, so we can control that, and the program will automatically from one run to the next one. Here at the bottom we see the run info, the description and logbook. So every run is documented. In terms of each run, there can be, of course, different calculation types: point calculation, grid map calculation, facade, meshed map, indoor, outdoor. And of course, for each of these lines, we have a set of parameters for the different standards. So we can duplicate one run and, for example, change the temperature or the humidity or other kind of parameters in terms of metrology that affect the calculation. So we can calculate different results for different temperatures, for example, or for different humidities to see how sensitive is this parameter. So SoundPLAN computes or predicts the level for a receiver. That receiver can be a single point. It could be a single point on a building with multiple floors. It could be a grid point within a contour map. The contour map can have thousands of receivers. And for each of these receivers, the program will scan the geometry for intersections. So it will send out a line, and it intersects with all the triangles for the ground model, intersects with the building, with the barriers, line sources, point sources that are within a certain search ray or search pi. And the program will put all of these objects that are found on that path into a list. By identifying the sources in that path, the program knows which standards need to be used. And then with that, how are the barriers, how is the distance, how is the elevation, and so on. How are they implemented in terms of the standard or the mathematical model of the standard. So it calculates all of these parameters in terms of distance, shielding, reflection, air absorption, some cases wind and speed or wind direction. And then after that path is computed, it notices that there is a reflection here. And then, of course, the program will create a mirror receiver and continues the path into this direction. So the reflective angle, the incidence angle is equal to the reflective angle. And it continues and finds, again, new objects, new barriers, sources, and so on, and continues that path. There are certain criteria when to end, how many reflection orders, or how far the path has gone. So a typical termination of the calculation is at 5 kilometers, but the user can modify those parameters. So after the program calculated 360 degrees around the receivers, the data will be saved and documented in the result tables. So all the intermittent results, spectral results, group results, all of that will be documented. Visualize the results in terms of receivers or contour maps in the graphics. We can create these single point results with tables, contour maps with the color-coded maps that visualize the topography or certain noise predicted levels for daytime, nighttime. There's also some results that can visualize the contribution, the sound level diagrams down here, bottom left here, that gives us the contribution. So each circle represents 10 dB. So we can identify the magnitude for each direction, and if the direction or the contribution is direct sound, the yellow lines, or red lines, which are reflected sounds. So these are various output options here in terms of the graphic with solid 3D model. There's also, in one case, measured data versus predicted data, or added to predicted data. And here we see also difference maps. Here other forms of results. I'll give you a variety of outputs, from topography to contour map, measured maps. So here there's a lot of flexibility in terms of these outputs. Here, just a quick visualization of the automatic documentation. SoundPLAN will document every single run in terms of the source documentation, the receiver calculated, what are the different levels of the documentation, could be for the source, the time, the frequency, the group, the propagation summary, the mean propagation, all the way to a detailed protocol. So where every single step is documented. In terms of optimization programs, we can have the program optimize. For example, the expert system will save for every receiver the contribution for all of the different sources. We can organize it by groups of sources too, where we apply noise mitigation for the entire group or noise mitigation for individual sources. And then here are different ways of visualizing what is the incremental contribution of each of the sources here. And then here we can see which of the sources have basically put the predicted levels over the limit. And then, of course, we can start mitigating those sources first and basically optimize the noise control with that. The same for the wall design. So here the wall design provides us the tool to optimize and iterate by wall size, by the height and the length, and the cost benefits. So we are doing a pre-calculation for a wall or berm. The program predicts the noise levels for the set number of wall elements or berm elements. The default is like 20. And it predicts it for each wall segment, for each receiver or facade point. And then it takes that pre-calculated file, which is a multi-dimensional database of receivers, barrier segments, barrier height, and assessment period, day, evening, night. We can define certain parameters or goals, and it iterates and it builds up that wall, the wall segment by wall segment, and selects always the wall segment that has the highest reduction for all of the receivers until the receivers get to the limit that they are assigned to. So here we can see like a graphic display here of the sound level, how it changes as the wall is built up. And of course, at the beginning, we get huge reductions, and at some point it flattens out. And that's basically what the optimization will show us. At some point, the program or the model, based on the standards, will show us that there is a diminishing return for increasing wall heights. And that's what we are trying to find out in terms of a cost-benefit analysis. Where is that breakpoint where we are just increasing costs, but we are not getting any benefits anymore? And of course, these results can be then saved back to the Geo-Database, and then we can run the model with the optimized wall. So the wall design is really a great tool to run various cost-benefit analysis with different maximum heights. And then with that, we can then later on run the models and get the final results. This ends the SoundPLAN software general overview on the principle, concept, and flow. Thank you for listening, and have a good day.